Hello and welcome to Engineering Economy. This is Dr. Ola Cameron-Diner. Today we will talk about choosing the best alternative. Specifically, we will discuss incremental analysis. We will talk about graphical technique in solving problems with mutually exclusive alternatives. And we will discuss using spreadsheets in incremental analysis. So the learning objectives for today are as follows. We will define incremental analysis. We will apply graphical technique in solving problems with mutually exclusive alternatives. And we will use spreadsheets in incremental analysis. So let's take a look at this interesting vignette. Tapping into controversy. Tappan Zee Bridge in New York opened in 1955. Design capacity of the bridge was 100,000 vehicles per day. An estimated useful life was 50 years. Original cost was $81 million. The current traffic in this example was 135,000 vehicles per day, clearly exceeding the design capacity by $35,000. Not $35,000, but 35,000 vehicles per day. So obviously, exceeding the design capacity is a dangerous thing. So therefore, there needed to be a solution. The two options considered was upgrading the existing bridge that cost over $1 billion, but the upgrading of the existing bridge will not adequately alleviate traffic congestion. And another option was building a new bridge at the cost of $4 billion. And that bridge would be 33% bigger than the existing bridge. And the possible additions would be light rail tracks, traffic-based toll collection. So if light rail lanes have to be included for environmental concerns, how does it affect the minimum cost of public works project? Another important consideration is electronic toll collection. Electronic toll collection can improve traffic flow, but there could be ethical issues in setting the toll. Should individuals pay a different toll based on income or number of people in the vehicle? Should toll change with time of the day or amount of congestion? What do you view as the primary ethical issues surrounding concepts like urban sprawl, eminent domain, and sustainable development? Let's discuss mutually exclusive alternatives. Mutually exclusive alternatives are options where there's only one alternative that can be implemented. Also, all alternatives must serve the same purpose. An objective incremental analysis is to select the best of these mutually exclusive alternatives. So incremental analysis, it could be applied to rate of return, present force, equivalent uniform annual cost, or equivalent uniform annual force approaches. And the way incremental analysis is applied is that higher cost alternative is represented as the lower cost alternatives plus the increment between the higher cost and the lower cost alternatives. So it's very interesting because the way the incremental analysis works, it could be kind of compared to, or we could use this metaphor of a boxing match, where the defender is the best alternative identified so far in the process, and the challenger is the next higher cost alternative to be evaluated. So what we're going to do in the incremental analysis, when we apply this incremental analysis, as I mentioned before, it could be applied to different, in different contexts. In the context of IRR, PW, which is present force, or annual cost, or annual force. So in all of those different contexts, what we're going to do is we're going to look at a set of n mutually exclusive alternatives, and we will rank these alternatives in terms of their initial cost, and then we'll get n-1 challenger and defender comparison that would be made from the possibility of n choose 2 or n multiplied by n minus 1 over 2 possibilities. So rather than doing a comparison of all possible challengers and defenders, we're only gonna look at the next higher cost alternative, the closest higher cost alternative compared to the um, lower cost alternatives. And we will start with the lowest possible cost alternative, which is often is represented by option of doing nothing. And so very often the investor have an opportunity to do nothing, and so that would be the lowest initial cost alternative. While some other projects would have some type of initial cost, and then we'll rank those projects in terms of increasing initial cost, and look at only the pairs that are they're placed next to each other in terms of this ranking. And so to make this whole thing much more clear, of course, right, the general slides does not, it provides some understanding, but to really understand things, you gotta apply it. So we can apply this in the example of incremental analysis. So we're going to use incremental analysis, and first we're going to use incremental analysis using graphical comparison. So we have two alternatives, the high initial cost alternative and the low initial cost alternative. So that's initial cost here in this row. When we subtract the two, we'll get this increment of $3,090. We have capacity, the high initial cost alternative has capacity of 150, while low has capacity of 100. So the increment is 50. The benefit, which is the annual benefit for high cost, is 4,000 per year. For low cost is 3,300 a year, and the useful life is always 5 years. So the difference in terms of the annual benefit, the increment would be 700 per year of extra benefit that's provided by the higher initial cost alternative. And the useful life is the same, so again, incremental and an incremental cost, we also have useful life of 5 years. If we were to find the present force for both of these alternatives, for high initial cost and low initial cost alternative, and plotted them against different interest rates, I, so you can see this is this denotes this horizontal axis denotes different interest rates I. For different interest rates I, we have the high cost alternative versus the lower cost alternative. These are plotted on this plot, and so here's a IRR for the high initial cost alternative, which is around 15%, and here's the IRR for the low initial cost alternative, which is slightly below the 20%. It's between 15 and 20%, and in this where they intersect together, that is the internal rate of return, or IRR, for in the incremental cash flows, or incremental incremental cash flows between the two. So now let's take a look at another example of incremental analysis using graphical comparison. Again, there's machine X versus machine Y. Notice the machine Y is a higher cost alternative with initial cost of 700 versus the lower initial cost of machine X, which is 200. There is a uniform annual benefit. This is also, there is a end of the useful life salvage value. And notice that these two machines have different useful life in years. So machine Y has a longer useful life. The machine X has 6 as a useful life. Machine Y has 12 useful life. So we could, for example, if we did use the present force analysis, we could, for example, use the least common multiple technique, which would assume that we could repurchase machine X again at the end of 6 years, and then use it with the same uniform benefit and the same useful life salvage value for the second life cycle of machine X. So using the present worst analysis, if we were to to use different eyes and then plot the functions, we'll get the following, right? So again, this is the higher cost alternative right here, which is machine Y. This is the lower cost alternative, which is machine X. And so they have corresponding internal rate of return. So this is internal rate of return of 15%. That's internal rate of return for machine Y. And here, where they intersect, that's the internal rate of return of the increment. So it's somewhere between 0 and 5%. So here's another example of incremental analysis of alternatives using graphical comparison. In this case, we have 3 different alternatives. They're all mutually exclusive, which means we can only select a single alternative. We can't do 2 of them or all of them. We only can do 1 out of these 3. And so we have the highest initial cost, which is C, and the next initial cost is going to be B, and then there's also lowest initial cost, which is A, and then they all have some uniform annual benefit. So if you were to find the net present worth of these alternatives, again, I don't give you the information regarding the years, but let's just look at the graphical comparison. So this plot represents these 3 alternatives, so different colors for different alternatives. So the lowest initial cost is right here. This is our A, alternative A. Then we have the medium initial cost right here. This in turquoise, that's B. For those of you that can see colors, and then blue. Right, the blue, that's the C, that's the highest initial cost alternative. So incremental analysis, right, compares the alternatives that are next to each other. So you would compare A to B, B to C, if you did that. So B is a higher cost alternative compared to A. So from B, we would subtract the cash flows of A. So again, from B, we'd subtract the cash flows of A. Here for initial cost and also for uniform benefits. And that will give us the internal rate of return right here, which would be represented by the intersection of the 2 curves, right? So this incremental cost are intersection of 2 curves, while the internal rate of return for specific alternative, for example, for this highest cost alternative, which is in blue, right? That would be its own internal rate of return of C right here, where it crosses, where the curve crosses the 0 line. And this is for B right here for medium initial cost. That's where B crosses the 0 line of net present worth of 0. And this is where A crosses, that would be the internal interest rate of A, where the A crosses the 0 level of net present worth. But the places where the 2 curves intersect, here for example, this is where C and B intersect. Gives us the internal rate of return of incremental C minus B. And this one where the B and A intersect, that gives us internal rate of return for incremental B minus A. And so it depends on a minimum attractive rate of return. As you remember, when we select the alternatives, we base it on minimum attractive rate of return. And that's the part that we discussed when we talked about rate of return calculations and choosing the best alternative based on rate of return if the minimum attractive rate of return is available. So if the minimum attractive rate of return is available, then we compare it to the internal rate of return of incremental analysis, right? So incremental, for example, B and A, we comparing alternatives allows us to compare alternatives B and A, incremental rate of return of C and B allows us to compare C versus B. So again, A is the lowest cost, the next low is B, so we're going to start comparing with B and A. In this example, we assume we're looking at these three alternatives. So we assume we know some minimum attractive rate of return. Again, to remind you what it is, and I discussed it previously in previous lectures, but to revisit, for completeness of information, the minimum attractive rate of return is a specific interest rate which a company sets for itself, and it wants to achieve this rate of return to satisfy some internal goals, maybe to be able to have some growth of its capital, whether it's investing the capital that it has in different projects. It wants to be able to get some kind of return on its capital, wants to see the capital that's invested grow at a certain rate, so it could, for example, fulfill some type of obligations or some type of expectations of its stockholders. So again, this minimum attractive rate of return is the lowest interest rate that the company expects its money to grow, right, at this minimum rate, at least at this rate or at higher rate. So if minimum attractive rate of return is larger than 9.6, then there is no interest in adding this additional money to pay for a higher cost alternative. Then we should go with the lowest cost alternative, which is A. So we're choosing alternative A because the minimum attractive rate of return is higher, right? So this 9.6 that we would get from this investing additional money into B is lower in this case, or less or equal, right, lower than minimum attractive rate of return. So we could just invest it in something else that would give us the minimum attractive rate of return. Therefore, we're going to choose A here. If the minimum attractive rate of return is between 9.6 and 2%, so if 9.6 is larger than minimum attractive rate of return, which this one, right, does not apply, right? Here, minimum attractive rate of return is smaller than, it's larger than 9.6. If minimum attractive rate of return is smaller than 9.6, if it's smaller than 9.6, but it's still larger than 2%, then we're going to choose alternative B. The reason why is because since minimum attractive rate of return is less than 9.6, we're getting more than minimum attractive rate of return by investing additional money into alternative B. However, because minimum attractive rate of return is more than 2%, or 2% is less than minimum attractive rate of return, there is no advantage into investing additional money into doing alternative C. Therefore, we're gonna do the B. So we choose alternative B. And then, if the minimum attractive rate of return is smaller than 2%, right? So, of course, the minimum attractive rate of return has to be more than 0%. But if it's smaller than 2%, so it's between 0 and 2%, then we're gonna choose alternative C, because alternative C is gonna give us 2%, which is more than our minimum attractive rate of return. So it depends on minimum attractive rate of return. This decision making scheme give us the decision of which alternative to choose based on minimum attractive rate of return. Of course, in this example, we do not consider an option of doing nothing. That would be an additional option if it existed. In this case, we have to do either A, B, or C. So now let's take a look at another example of incremental analysis using graphical comparison. And how can we do with the graphs? Just a quick question to you. Well, we could use Excel to graph it for different values of I, right? We could plot different values of I based on these values of I, we could determine present worth using the PV function in Excel. So then it would allow us to plot these different alternatives. So in fact, we could have these different brass, stainless, and titanium as mutually exclusive alternatives. We can either go with making it out of brass, or making it stainless, or making it titanium, or ordering a brass equipment, stainless, or titanium. And so there are different costs, brass being the cheapest, titanium being the highest initial cost, and then they have different useful lives. Of course, if we were to look at the useful lives, if we try to use a least common multiple approach, it probably would be kind of difficult, because the least common multiple for all of these would be 100 years, which is quite long. And instead of using present worth analysis, therefore, we're going to use equivalent uniform annual cost. So instead of this, we're just going to represent it as equivalent uniform annual cost. And so using that kind of analysis, we're going to get the annual cost of each of the alternatives. We can plot them again against different values of I. And so here you can see, right, this is a brass, right? This is the lowest initial cost alternative. And then this is a stainless, this is a medium initial cost alternative, and here's a titanium, which is the highest initial cost alternative. So then when we compare just equivalent uniform annual costs, again, wherever these curves intersect is where we're gonna get our values of internal rate of return of incremental differences, or differences between two alternatives. For example, this intersection right here that I just showed, it's the one that gives us internal rate of return of incremental analysis of titanium and stainless. So choosing between titanium, which is a higher cost, and stainless, which is a lower cost in this case. So in fact, right, this is 6.3%. It's internal rate of return incremental between titanium and stainless options, with titanium being the higher initial cost, stainless being lower. Right here, that's stainless versus brass. So stainless here is a higher initial, because brass is lower in initial cost than stainless, and that's 15.3%. So we don't really need to consider this one, because we're only selecting the ones that are next to each other in terms of the initial cost. The brass and titanium is not next to each other. The brass and stainless, they are, and then stainless and titanium, they also are next to each other in terms of initial cost. And see, here we rank the initial cost from the lower to the highest, from the lowest to the highest. So then these two values give us the, right, so we disregard this because this compares the two alternatives that are far away in terms of initial cost from each other. So we only consider this and this in our decision making. And so we would select, right, so we would start with brass, right, and we would see if minimum attractive rate of return is going to be larger than 15.3%. There is no advantage in going with stainless, so we would select brass. Right, so, and if the minimum attractive rate of return is less than 6.3%, then we would select the titanium, because titanium would give us more than 6.3%. So that's what this rule says. So this rule says if minimum attractive rate of return, which is always more than 0%, if it's less than 6.3% incremental rate between titanium and stainless, we're choosing the higher initial cost alternative of titanium. Then if it's actually lower, right, if minimum attractive rate of return is lower than 6.3, we chose titanium. If minimum attractive rate of return is higher than 6.3, then titanium would give us 6.3, but the minimum attractive rate of return is higher, so we're not interested in titanium. We're gonna go with stainless as long as the minimum attractive rate of return is smaller than 15.3%. Then we choose stainless, and then if minimum attractive rate of return is more than 15.3%, then we're gonna choose brass. Because in this case, right, going with stainless, we only get 15.3%, but MARR would be larger than 15.3%, so we're not interested in investing additional money into stainless. Instead, we'll just go with brass. So now let's take a look at an incremental analysis that does have do nothing option, because before, all those examples that we just looked at before, they did not have do nothing option. So in this case, we have machines X, Y, and Z, and we also have a do nothing option. Notice that machine X is the lowest cost, initial cost alternative, then machine Z is the next in terms of the cost. It's higher than machine X, but lower than machine Y, and machine Y is the highest initial cost alternative. So we would have do nothing, then machine X, then machine Z, then machine Y in terms of increasing of initial cost. That we ranked 4 alternatives because in addition to machines X, Y, Z, 3 different machines, we also have do nothing. So therefore we have 4 options. So we rank these options in terms of increase of its initial cost from do nothing to machine X, then machine Z, and then machine Y. So we're going to plot these. How do we plot these? Again, we're going to use Excel. We have different values of I, say 0%, 1%, 2%, and so on. So we can plot these curves. We can plot these curves using different I's, and then using the values, we can find, and using the Excel functions, we can find the payment using PMT Excel function. We can find the equivalent uniform annual worth for different machines. So we have 3 curves for 3 different machines in 3 different colors. For those of you that can see colors, of course. And then machine X is this. Right, if you don't see the color, this is machine X. This is machine Z. The next higher cost alternative is machine Z. This is the machine Z. And then last but not least, we have machine Y, which is this is the highest cost alternative. So now, which one we're going to compare? First, we're going to compare machine X to do nothing, because do nothing is the lowest cost. So machine X is right here. Do nothing means 0. So this is where machine X curve intersects 0 annual worth, right? Or just 0 level right here. So this is a little bit below 25%. So maybe 23.5 or something like that. Well, actually 23%. Right, so now we have internal rate of return for X is 23%. That's also the same as internal rate of return of X, incremental of X minus do nothing. So as long as minimum attractive rate of return is more than 23%, we would do nothing. Because the X, the lowest cost, still does not satisfy our a high minimum attractive rate of return that's higher than 23%. Next, we're going to compare machine X with machine Z, because the machine Z is the next highest higher cost alternative. So then, where do they intersect? They intersect right here, right? This is machine X curve, this is machine Z curve. They intersect here. This is the point that gives us incremental rate of return of machine Z minus machine X. In fact, that falls under 11%. So this this intersection here of curves of annual worth of machine Z minus machine X, or with the machine X curve that gives us incremental rate of return of Z minus X. That's at 11%. Therefore, we're gonna go with machine X as long as minimum attractive rate of return is between 11% and 23%. And then, and then we're looking at the next level. So machine Z, right, is compared to machine Y, because machine Y is the next higher alternative after machine Z. So where do these curves intersect? They intersect right here at this point. This is machine Z, and this is the machine Y. So that's their intersection right here, and that gives us internal rate of return of 3.5% incremental between Y and Z, Y minus Z. So as long as minimum attractive rate of return is between 3.5% and 11, we're gonna select machine Z. But if minimum attractive rate of return is smaller than 3.5%, then we can actually implement machine Y or use machine Y. So exactly like I said, if minimum attractive rate of return is larger than 23%, there is no advantage in investing money into X, because we're getting less than what our minimum attractive rate of return. So we're gonna go ahead and do nothing. If it's between 23%, we could invest in X, right? If it's a minimum attractive rate of return is smaller than 23%, we're getting this 23% that's larger than MARR, so we're benefiting from investing the money into X, as long as the minimum attractive rate of return is larger than 11%, because at 11% is when we actually can invest. If it's higher than 11%, we can invest in Z, which is a higher rate. So if it's between 11 and 3.5, you're going to choose Z, and if it's more, well, that's supposed to be 3.5 here instead rather than 2%, so keep in mind this is not 2, scratch that, this is supposed to be 3.5 here, that's a misprint. So if 3.5, if minimum attractive rate of return is smaller than 3.5, then we choose Y. Now let's take a look at this example, but without do nothing option. If we do it without do nothing, again, we have 23%, 11%, and 3.5% for the incrementals. Then we would choose X anytime that minimum attractive rate of return is larger than 11%. So if minimum attractive rate of return larger than 11%, we choose X. If minimum attractive rate of return is between 11 and 3.5, we choose Z. And again, this is supposed to be 3.5 rather than 2. So I corrected this, right? So now you can see I corrected this. So here we have 3.5%. So if our minimum attractive rate of return is less than 3.5%, we're going to choose Y, right? Why? Because Y is a higher initial cost alternative. And then we actually had, I also corrected the previous example where we have with do nothing option, right? So let's go back and look at the with do nothing option. I changed it here to 3.5 because of course this is our internal rate of return. This should be 3.5. So if we compare the two, the only difference is that before we had this do nothing, so now that it's not available, we don't have this differentiation with the 23%, right? We just simply have minimum attractive rate is more or equal than 11%. So, but when we had the do nothing option, we also need to take into account this internal rate of return for the lowest cost alternative, because it also represents the incremental rate of return between X and do nothing. But without the do nothing option, you can see that all we have is this whether the X is better than the Z, right? And if minimum attractive rate of return is more than 11%, then X is better than Z. So we don't really take into account this because we just simply don't have the do nothing option. We gotta choose one of these X, Y, or Z, and if we don't have the do nothing option, then then this becomes irrelevant. This rate of return for X becomes irrelevant in the decision making. All right. So now that I've fixed the and corrected the values here, you can see how it works. Again, it was using the same values for machine X, Y, and Z as before. The only difference was that now we didn't have an option of doing nothing. We had to choose to use one of these three machines. So here's another example of incremental analysis using graphical comparison. And this one has even a larger number of mutually exclusive alternatives. So you can see we have option A, B, C, D, and E, and they're not ranked here, right? A, B, C, and D they're not ranked in terms of initial cost. If you were to rank them, we would start with D, then it would be B, increasing initial cost, then it would be A, increasing initial cost, then C, even higher initial cost, and the highest initial cost would be E. So it would be D, B, A, C, E. And of course, it depends whether we have do nothing. If we had do nothing, then it would start with do nothing rather than D. So here we're plotting their net present worth. The net present worths are plotted. They're all correspond to different colors. So I'm gonna name them or show them for those that do not see colors too well or might not see this plot too well. So again, we start with the lowest initial cost. This is our D right here. Then the next one is B. Here's the B. And then we have A. This is A. And then we have C, which is right here. And then we have D, sorry, not D, we have E. D was the lowest cost if we don't take into account nothing. And then we have E, which is right here. That's E. All right, so what we want to do here is we're going to compare, right? If you're comparing D to do nothing, we would look at where the D intersects the level 0. Otherwise, we would compare D to A, sorry, not A, to B, because D and B are next to each other in terms of initial cost. And so it would be B minus D because B is the highest cost, so B would be the, D would be the defender, and B would be the challenger. And so B minus D, it is found where B intersects D. So you can see this is a B here, and it intersects D somewhere there. And then we compare next B with A. So B would be the defender, and A would be the challenger, and so on, right? Of course, if B is going to be better than D. So this one is a little more complicated. So we find first for B, right? This is the internal rate of return. This is difference between A and B. This is a difference between C and A. So graphically, we would look at the ones, right? So rather than looking at all different options, we would look at the ones that would give us the highest net present worth. So that would be this here. You can see this is the highest net present worth. So the B would actually defeat C because B is always above D, pretty much. And we would choose the B compared to do nothing, and then right, because below do nothing, both of those D and B, they're below do nothing. So B is above, so that would means that we choose B to do nothing. The then we would have B at for 20% as long as minimum attractive rate of return is more than 20%, we would do nothing. And then if it's between 20 and 11%, we would choose B. And then the next one after B would be A, and so A would be the challenger, and A would be advantageous as long as we were between 11 and 2%. And then the next one after A would be C. So C would be better than A if our minimum attractive rate of return was smaller than 2%. And that's exactly what we have in terms of the decision rules. So now here's another example. We have A, B, C, D, E, the same costs, the same data as we looked at the previous example. The way to do it in terms of using pairwise comparison rather than graphical computations. So if we don't go with the graphical computations, then we use defender-challenger comparisons, which means that we would need to perform n-1 comparisons. In this case, if we use do nothing, then it would give us, n plus the 5 alternatives that we have, it would have us altogether 6 different alternatives. So 6 minus 1 would be 5 different comparisons. So we would start first, right? So this is without relying on graphical analysis. So without relying on graphical analysis, we would rank the alternatives in terms of increase of their initial cost, starting with a lower initial cost and going all the way up to the highest initial cost. So then, as I mentioned earlier, we would rank it as D, B, A, C, E. And then we would compare D, right, and compare it to doing nothing. Right, so we rearrange alternatives in order of increasing costs. Then we calculate internal rate of return of least expensive alternative to see if it's better than doing nothing and minimum attractive rate of return. Right, so in this case, we're actually given the minimum attractive rate of return, and so we are using minimum attractive rate of return. So in this case, rather than setting up a decision rule that's based on graphical analysis, we are already given the minimum attractive rate of return, and now we are using comparisons in terms of this defender and challenger to figure out which alternative we should go with. So our specific minimum attractive rate of return is 10%. Right. So again, let's take a look at do nothing to compare the least expensive alternative, which is D, to do nothing. We compute the internal rate of return of D, which would be the same as incremental return of D minus do nothing. So if you look at the internal rate of return, we're setting it up as follows. This is the 10 present worth of 1,000, right, in terms of the cost, negative cost. It's still going to be present. This is the annual, so we multiply it by discount factor of P given A. And in this case, we have N being 20 time periods or 20 years. And this is our internal rate of return of D. So from this, we just solving this equation where present worth of D is set to 0. We're solving this equation from which we're going to determine P given A. And then from the value of P given A, we can determine the value of the rate, or internal rate of return of D. And that would be using interpolation. We will get 9.94%, and that's less than 10%. So if the doing D gives us less than minimum attractive rate of return, if the return on D is less than the minimum attractive rate of return, there is no advantage in doing it because we could invest it in some other projects that would give us our desired minimum attractive rate of return. So we're not going to do D, we're just going to do nothing in this case, right? Nothing is preferred, And so nothing remains a defender because the challenger D failed to defeat do nothing, so do nothing is still the defender. And so then we compare the next alternative to do nothing. The next alternative in terms of initial cost is B. So you can compare B to do nothing. So we can calculate internal rate of return of the next alternative B to see if it's better than do nothing at minimum attractive rate of return of 10%. So again, notice we had negative 2,000 in terms of the cost in the present, and then uniform annual benefit of positive 410. So we're just gonna replace this with 2,000 and this was 410, but the same remains except this is gonna be internal rate of return of B, and that's gonna be the present worth of B. So that's the same. So in fact, right, this is a negative 2,000 of the cost, this is 410 of annual benefit. To make it in the present, we multiply that by P given A. And from this equation, we can determine the P given A, and from P given A, we can determine internal rate of return by maybe plugging in some values of rate of return and then interpolating. So what we get is 19.96%, and this 19.96% is more than 10%. So it's more, the rate of return of B is more than minimum attractive rate of return. Therefore, we're gonna go with B. Alternative B is now preferred to doing nothing. And so this becomes, alternative B becomes the new defender. So next we're gonna compare alternative B to the next alternative in line. The next alternative in terms of initial cost is A. Right, just to show you, let's go back. After B, we have A in terms of the rank of increasing initial cost. So we're going to compare B and A. So now it's not going to be IRR of B or IRR of A. It's going to be IRR of A minus B. We're subtracting from higher initial cost A, we're going to subtract B. So we're looking at present worth of incremental A minus B. So incrementally, the cost of 4,000 minus 2,000 and the benefit of 639 for A minus the benefit of B of 410. And of course, the annual benefits need to be discounted to present from the annual series, uniform series to the present by multiplying by the discount factor. And here the rate of return is incremental between A, which is a higher cost, and B, which is a lower cost, over again the same 20 years. So now, right, these two simplifies to 2,000, negative 2,000. This simplifies to 229. And so we divide 2,000 by 229 to get P given A. And then from the value of P given A, we can try different rate of returns to find the incremental rate of return of A minus B through possibly interpolation. And in fact, through interpolation, we get that a rate of return incremental between A and B is 9.63%, which is just below 10%. So this incremental rate is less than minimum attractive rate of return, which means that we are not interested in investing additional money into A because those additional money would not gain the minimum attractive rate of return of 10%. It would have a smaller rate of return, and so we would be better off investing those money that would go towards A, towards some other alternative. So alternative B is still preferred, it's still the defender because A failed to exceed this minimum attractive rate of return. And next one is to compare B with the next higher after A, which is alternative C. So this comparison is again an incremental comparison, so C minus B, again 6,000 minus 2,000, and then 671 is a uniform benefit for C minus the uniform benefit of B, again P given A. So it's pretty much the same as what we did in the previous step. The only difference is now we're comparing C to B. So we're comparing C to B. So again, the same way we can solve it, do the interpolation, get the internal rate of return between C and B of 6.8 hundredths %, which is lower, right, significantly lower than minimum attractive rate of return. So there's no interest in investing those additional money into C because it's not gonna gain us this minimum attractive rate of return of 10%. It will be a much lower rate of return. So alternative B is still preferred and still a defender. And then we can compare B to this last one, which is alternative E. It's the highest initial cost. And again, we are making this comparison incrementally. So it's going to be E, which is the highest cost, minus B. So we're going to look at present worth of E minus B, set it to 0, and then find the incremental rate of return of E minus B from that. So in fact, present worth of E minus B going to set to 0. We compute the present worth of E minus B. This is the initial cost in present of E minus the initial cost of defender B, right? The B is lower, so we subtracting the B. And here's the same for the annual cost. And then we need, because we're finding the present value of this annual cost, we multiply it by the discount factor. And so from this equation, we can find the discount factor P given A, and then plug in different values of return or interest rate. We're going to get an incremental rate of return between E and B through the interpolation. And that's just a meagerly 0.67 thousandths %. And that's, so 67,000% is quite low. So there's definitely no reason to invest additional money into E. Because it's much lower than the minimum, or anyway lower than the minimum attractive rate of return of 10%. So B still remains the champion, and E has been defeated. So B is the alternative. That is our final selection. That's our champion. That's the alternative that we should select. So now what I wanted to do is quickly go back, right? So alternative B, we did all these comparisons and we found that alternative B is preferred. Now let's go back to the graphical analysis and look at why we might how we got the alternative B if we were to apply the rules from that analysis. So again, remember the minimum attractive rate of return is 10%. And this is a slide that previous slide that shows the graphical comparison for the same alternatives. So remember in that example that we just finished looking at, and the minimum attractive rate of return was 10%. If we plug the 10% in this rule, the 10% would fall into this bracket where the minimum actually, maybe the A and the difference between A and B, which is shown as 11% here, maybe some of the values is not correct. Maybe this wasn't the 11%. Let me double check the values. So in fact, we do see that when we look at internal rate of return between A and B, it was below 10%. So when computing it more precisely, we got 9.63%, which were from the plot, it looked more like 11%. And that's one of the difficulties in terms of the plots, right? You would still want to double check and compute the points, because sometimes from the plot you might look at it and say, well, it looks like 11%, but doing the computations and finding it more precisely, if you would actually get that A minus B is not 11%, it's in fact 9.63%, which is less than 10%, and therefore the B is the alternative that we should select. So that highlights the need for more precise analysis in support of your graphs, right? So the graphs are really useful in terms of determining the rules, but to be sure, you always would want to do the incremental analysis to double check whether what it looks like on the plot, whether because again the plotting might be less precise if you're using intervals or rate of returns, i's at larger intervals. The curves might not be very precise, so make sure that you double check the points by computing the specific interest rates for those points. So there you would want to make sure that you compute a minus b, and also some of the other ones that to determine whether we found the precise points. All right, we can now summarize what is required in terms of being able to compare mutually exclusive alternatives. First step would be to identify all alternatives. That means that we would need to look whether we can do nothing or whether do nothing is not an option. Then we need to construct either a net present worth or equivalent uniform annual worth graph showing all alternatives on the same axis. And then we want to examine the line of the maximum values and determine which alternative created it and over what range. We also want to determine the changeover point. And just like I emphasized just a little bit ago, or immediately preceding discussion, emphasized that it's important not only simply look at the graph and eyeball the changeover point, but also compute it to make sure that what you see on the graph is actually, you can get the precise value or get the precise value for the graph. So you want to determine the changeover point, which could be either a point of intersection of two lines, right, or two curves, one of which is the line of maximum values, and the other one would be the option where we have an intersection of a line with the zero level, right? So the maximum value was the zero level, because again, we don't want, if we have the do nothing alternative as one of our alternatives, we do not want to have a loss. And if we have something less than zero, then that would be a loss. So in that case, the do nothing would be preferred. And finally, we can create a choice table to summarize information. And that's what we had before, those decision rules, or a choice table, where it would depend, our selection would depend on minimum attractive rate of return. So again, these are the 5 key steps in comparing mutually exclusive alternatives. So we can also look in terms of choosing an analysis method, and all analysis methods provide consistent solutions. We could use either rate of return analysis, and advantages of this method is that it's easier to explain, it's most frequently used in practice. However, there are some advantages. In particular, it requires additional effort in terms of calculations, so it's more difficult to calculate, at least without the spreadsheet. But then it also does not require a minimum attractive rate of return in calculation, and that's a big advantage of the rate of return analysis. And in terms of using present worth or annual cash flow analysis, these methods, they require known minimum attractive rate of return calculation, but on the other hand, they are easier to calculate without using Excel. So now let's take a look at using Excel and discuss some functions that could be useful in incremental analysis. And these are basically 2 functions. One is rate function in Excel, And this rate function allows us to find rate of return or incremental rate of return given the specific values of either uniform equivalent amounts or present wars or future wars. Again, the type denotes the choice of whether we are selecting to use or choosing to use end of the period assumption or beginning of the period assumption. And by default, it's the end of the period assumption. And the guess is some numerical value because, as we discussed in some of the previous chapters, there could be multiple rate of return values. And so the guess is where you would initialize Excel to start looking for the solution or the root. And then in terms of internal rate of return, again, we can have a range of values, and that allows us to find internal rate of return of a series of cash flows that are given in this range in Excel spreadsheet. And guess, again, is sometimes useful in terms of being able to select a single value if you have multiple roots. Also, another things that could be useful when doing incremental analysis are these Excel tools such as GoalSeek and Solver. And the GoalSeek, it varies the values in one specific cell unit of a formula that's dependent on the cell returns of the wanted result, while the Solver adjusts the values in the changing cells to produce a result from the target cell formula. And then constraints are applied to restrict the values that Solver can use in the model. So all of these GoalSeek and Solvers, they kind of allows us to do some optimization or some type of analysis. All right, so that's it for choosing the best alternative, and I look forward to seeing you again.